In this video, we will look at filtered back projection, which is a really basic and quite old now image reconstruction technique based on the model of the radon transform or the X-ray transform. And for that, we're going to look in detail, very mathematically and visually. We're going to be looking at the central section theorem, which is the mathematics behind filtered back projection. So I'll be using the example of positron emission tomography, where we have some radioactive distribution, for example, in the brain here. This is fluorodeoxyglucose as a simulation. And we've got some function f, for example, radioactive concentration f, depending on x and y. So that's the x coordinate and the y coordinate. And then what we typically obtain would be a sinogram where we have a number of measured counts m, depending on some position s and a viewing angle phi on a sinogram. So I'll quickly review what I mean by that. In PET, we have these back-to-back photon pairs arising from positron-electron annihilations in the field of view of the scanner. And if we look at one particular pair of annihilation photons coming from a positron-electron annihilation, then what we can do is characterize the line through the field of view, which we call a line of response. We can characterize that line by taking our xy coordinate system, rotating it by a viewing angle phi, and so when we rotate the xy system, we call it S and L. And then the benefit of doing that is that we can then characterize that line quite easily by saying, well, okay, it's parallel to this L axis, and therefore S gives us the perpendicular distance of this line from the center of the field of view. So for this case here, it's a short distance of 5.5, and we can also characterize that line of not just by S, but of course we need to know what was the rotation angle of the XY coordinate system in order to get L parallel with the line and S being perpendicular. Basically, S and phi tell us about that line through the field of view. So I can therefore look at the sinogram and say, okay, a position S and a viewing angle phi, that line through the field of view corresponds to a particular sinogram bin. I've exaggerated it here with this large red circle, and so we can relate any line through the field of view with a particular location or bin on a sinogram. Now, what happens is that over time, of course, there'll be many positron-electron annihilations, and we'll have back-to-back photon pairs given off isotropically from this distribution. But over time, if we just fix our attention on that one sinogram bin, in other words, that one line through the field of view, then of course there'll be many annihilations that occur along that line, and they could have originated from any of the various positions along that function f that actually sit on that line. And so over time, as we acquire data, we end up with effectively a value m which is proportional to the sum of the activity along that line. Okay, so that means we can therefore model a sinogram and how the sinogram function here m relates to the original function f of SL, or indeed f of x and y. And so for that we use what's known as the 2D radon transform, or indeed the 2D X-ray transform, because it's worth saying that this methodology is also applied in computed tomography in CT as well. And so maybe that's also why we use the terminology 2D X-ray transform. So what we're saying is that we can relate what we're wanting to find, the function f of S and L, which is here, we can relate it to what we actually measure, the sinogram, through simply a line integral equation. And so I'm going to demonstrate how we can do this model by showing, for example, here a number of different parallel lines through the field of view. And we know, of course, that these lines are characterized by a distance s and by a viewing angle phi. So these ones here correspond to a viewing angle phi of 0. Okay, so if you had that SL system back where it started, if phi is equal to 0, then it would line up with the XY coordinate system. And what we can do then is just collect a set of line integrals, of projections of that distribution for different positions S for that fixed viewing angle phi. And then all we have to do is just consider all of the various lines at all the various rotation angles and simply sum f of xy along those various lines through the field of view. And so that's what this equation does, is it models a sinogram and how it relates to the function f that we would like to reconstruct from the function m. And that's what this video is all about. How do we go about finding f when actually what we have are this set of line integrals. Okay, this is just another schematic just to really drive the point home. Here I've now got a very simplified function, f of xy. It's this kind of rectangle function here, and I'm showing a particular viewing angle phi of 45 degrees. So the xy coordinate system gets rotated by 45 degrees to give this SL axis, and then we just sum along the direction L. So we're integrating along the direction L of the function f of s and L, because of course f of xy could also be expressed as f of s and L. Do the summation along L, and that gives us a model of the sinogram. Now, of course, it's only a model because in reality this would be a finite number of counts m for each sinogram bin s and phi. So just to depict that again, just showing that I can do a set of line integrals in order to predict, to model what the sinogram would look like for a given function f of x and y. So now we're going to get into how we go about reconstructing f when what we have is a sinogram m. So there is that expression for the sinogram, the radon transform, 2D X-ray transform, except here I've just shown phi now as a subscript because I'm just going to consider a 1D function. This is called a 1D parallel projection, a value m depending on distance s, where phi here is fixed, and I'm just showing the example of phi is equal to 0. So that's what we've been dealing with before. And then I'm just going to show the definition of the 1D Fourier transform of this function m of s. And to do the Fourier transform, all we do is just multiply by a complex exponential, integrate to give us the amount, capital M, of frequency ks that is present in the function m of s. That's all the Fourier transform is doing. And then we can substitute the expression for the line integral, the radon transform, the X-ray transform, back in to this definition of the Fourier transform to arrive at this expression here. All very good. But why are we doing that? Well, if we independently now consider what we actually are looking for, which is the original object, or if you like in quotes, the image that we're trying to reconstruct, f of s and L, and if we were to define the Fourier transform, the 2D Fourier transform of that, then of course we take f of s and L, multiply it by a complex exponential, a 2D one, integrate, and that gives us the amount of spatial frequency ks, kl, the amount f of that frequency that is present in f of s and L. So we could do that for all the various spatial frequencies and build up a 2D function, 2D k-space, representing the object that we're trying to reconstruct. So this is how it might look like. This is a 2D k-space. Often it has a peak in the middle, lots of low spatial frequencies. Here, though, I'm showing the absolute value of f and then also taking the logarithm just to improve visibility of the Fourier transform. Now, having written down this, basically the definition of what it is that we don't know, because we don't know f, but if we did know f, we'd be able to show the Fourier transform of it. The reason I've done this is we can compare what we want with what we have, which is on the right-hand side. So let's do a comparison. If you compare these two terms, you'll notice that they're actually identical when KL is equal to 0. Okay? And so that shows us that the following is possible. If I take a 1D parallel projection, that's m phi s, if I Fourier transform it, then if I Fourier transform it, I get an expression that directly matches the 2D Fourier transform of what we want, except it's just a central section because KL is going to be equal to 0. So we have, if you like, the KS axis here. Remember, we've been dealing with the XY coordinate system and then rotating it to get SL. Well, likewise here in K space, we have KX, KY, and then if we rotate it, we'd have KS and KL. Right, so let's see then if we take the Fourier transform of this to get capital M of KS, then that gives us information for when KL is equal to 0 at the origin here. This is a function of KS. It gives us this part of this 2D function, because this line here depends on KS as well, and we know those expressions are equal along that line. So I've put the axes on there, KS, KL. If I remove the axes, if I Fourier transform that, that allows me to find a set of values, capital M, with which I can populate that line, that central section in the 2D K-space of the function I'm wanting to reconstruct. So then I can do the same thing for all the various viewing angles. I could go to the next viewing angle, and that corresponds to a slight rotation of an angle phi, of course. So the KS, KL system is just rotated slightly, and so now KS would be along this azimuthal viewing angle phi, corresponding to the increase in azimuthal phi angle here on the sinogram. So Fourier transform that gives me another central section through K-space. Keep going, increasing viewing angles, Fourier transforming each and every 1D parallel projection. If I Fourier transform, I get central sections. There's a slight misalignment here. That's pi over 2, 90 degrees. So that should be halfway along this phi axis. But you get the idea. This is an illustration. I'll be giving you an accurate video animation in a moment. And so by taking all the 1D Fourier transforms here, I can populate the two-dimensional Fourier transform of the function that we're trying to find. Now you'll notice the sampling density here is not uniform. It's like spokes intersecting, and so we get a kind of a 1 over r, a kind of a 1 over magnitude of k, if you like, sampling density. So we've got a large number of samples in the middle and sparser samples at the ends of our populating of k-space here. So that means before taking the inverse Fourier transform of this to find what we want, we've actually got to normalize for those varying contributions. So I've shown here that with this kind of, these intersections where they all coincide at the origin, we end up with this kind of 1 over magnitude of k, where magnitude of k corresponds to the distance of any particular k-space point from the origin. We get this 1 over magnitude of k sampling density, and we correct for that using what's called a ramp filter, because to get uniform sampling density, we'd have to multiply 1 over magnitude of k simply by the magnitude of k. So that means the further out this is, the more we amplify it to compensate for the fact there have been fewer contributions in the 2D K-space. So that can be done here in the 2D K-space using a 2D ramp filter, and then we could inverse Fourier transform that and find what we want. Or, and this is what is done in filtered back projection, equivalently, we can just do a 1D Fourier transform of each row of the sinogram, each 1D parallel projection. We can then do a 1D ramp filter where we do that amplification according to the magnitude of k. And then once we've done that, we inverse Fourier transform that, and then we can back project to get a reconstruction. Okay, so we'll be visualizing this process in detail in the coming few animations. Okay, before we get to the animations, just to show another schematic here, using a simplified version here where I've got that simple case again. What we're saying is that we take a 1D parallel projection, Fourier transform it, that gives us a K-space line, and that is equal to this central section through the 2D K-space of the original function f of x, y. So that's a very simple graphical illustration. Okay, this is where we're going to be headed. By the end of this video, I will graphically demonstrate the central section theorem for this brane distribution, the simulated brane, and the sinogram, where we're taking 1D Fourier transforms of each of the rows, that's shown there, 2D Fourier transform of that, and I'll be showing explicitly how these two relate through an animation. But before that, to understand it more clearly, I'm going to start off with this very simple case of a point source distribution, whereby if we take a Fourier transform of a point source, a delta function, then we end up with a completely flat function. And likewise here, if we consider the sinogram for that point source, well, we know if we take the projection, so remember there's the x-y axis, And what we can do is take projections by rotating that xy coordinate system to get the SL coordinate system and do the line integrals. Well, when phi is equal to 0, then we'd just be taking vertical line integrals here. And then at the origin, we'd end up with just a simple delta function, because the function is 0 here, 0 here. It's only got a value here, so therefore we get a projection value at the origin. Okay, so the forward projection of that to get a 1D parallel projection is a delta function. And in fact, whatever the viewing angle there, we'd get the same single delta function, a single count at the origin of the parallel projections, whatever the viewing angle phi. And of course, therefore, because this is just a stack of 1D parallel projections, each of which is just a simple delta function, when we do the Fourier transform of each and every row of the sinogram, this is why I've called this the 1D Fourier transform, just doing the rows, then because each of these are delta functions, each of these are just flat constant functions. Okay, so another way of viewing that is to say, well, if we had all of the values in k-space here, as shown in this k-space line, if we were to inverse Fourier transform that, we'd get a delta function, because you add together, for example, all the cosines, they all coincide at the origin to give you just a delta function, and all the tails cancel out. But anyway, let's get graphically now into an example of this. Okay, so now I'm going to graphically illustrate what's going on in k-space. I'm starting off then by visiting the center of that 2D Fourier transform, the 2D k-space, and I've got a little dot here to show which part of k-space I'm visiting. And what I'm going to do is just visit various values along a line in k-space. Anyway, at the origin, that's the center of k-space, so kx, ky equal to 0, and that corresponds to a cosine and a sine basis function, a pair of basis functions. When kx and ky are equal to 0, cos is just 1, sine is 0, we just have a flat function only. And what I'm doing here is just showing the Fourier synthesis, in other words, the inverse Fourier transform of just a center point in k-space gives a flat function. Okay, and then also here I'm going to be showing that center of k-space corresponds also to the center of this k-space line, which is found by the 1D Fourier transform of a given row of the sinogram. So let's move on to make this clearer as we go. First of all, then, I'm visiting the next location along the kx axis. That's kx is equal to 1. Therefore, I get one cosine function fitting within that horizontal field of view, if you like, of the scanner. So cos kx is equal to 1 times x gives one cosine function. The sine, we get one sine function. And then what I'm doing here is I'm just adding those together. I'm doing, if you like, the inverse Fourier transform of those 2 points in k-space, and I end up with this being effectively a flat offset plus a cos and a sine added together, and you end up with a kind of slight phase shift in the overall Fourier synthesis, the summation of those two spatial frequencies. K is equal to 0, kx is equal to 1. And then here I'm showing the same but with no negatives, because what I'll be doing here is building up the overall Fourier synthesis, the overall inverse Fourier transform. Here I'll just be showing the inverse Fourier transform of any given line that I'm considering. Let's move on to make this clearer as we go. So if I go to kx is equal to 4, as I progress along this kx axis, I've now got 4 cosines, 4 sines. I'm adding these together by using the values in this 2D k-space. Remember, this is capital F as a function of kx and ky, or ks and kl. And the capital F tells me, as a complex value, it tells me how much of the cosine, how much of the sine to use, to add together when I'm doing the image domain representation, in other words, the Fourier synthesis or the inverse Fourier transform. And what this is saying here is just take the same amount of every single spatial frequency. So I take the same amount of this, same amount of that, add them together to the growing picture, because I've also considered earlier kx values. As I add them together, I get this result. And if I clip the negatives, I get that result in the top left corner. Let's keep going to higher and higher spatial frequencies. In other words, more and more of these waveforms are fitting within this interval here. And you'll notice, of course, that these are all vertically along the y-axis absolutely identical, and that's because ky along here, that's the ky axis, kx axis, ky is equal to 0, which is the zero frequency, which is a constant function. So these are constant in the y direction. Okay, let's keep building up to more and more positive kx values. So I'm adding together all of these high spatial frequencies. And you'll notice that I'm getting this nice kind of coincidence, this kind of constructive interference of all these cosines and sines in the middle here. And then the tails are cancelling out. Okay, just an observation. So we're getting this nice kind of build up in the middle. And now let's consider the negative spatial frequencies. When I've got the negative kx, cosine looks the same for negative and positive spatial frequencies. Sine, though, you get the negative of the sine function, because sine minus x is equal to minus sine of x. It's an odd function. Cosine is an even function, so it looks the same. Anyway, I'm doing the same process here of adding together these spatial basis functions. So kx is equal to minus 6. I get 6 cosines, 6 sine functions. Again, you notice it's the negative now of the sine due to the negative frequency. Let's just keep progressing in the negative spatial frequencies. These are all nicely adding together, coinciding in the middle. Tails are cancelling out. And let's get to the so-called Nyquist frequency, which is the maximum possible frequency I can represent, because this is a 128 by 128 discrete example. So I can fit in a maximum of 64, that's kind of up, down. 64 cosines can be fitted in along that direction. Sine here is 0 for the Nyquist. And you'll notice that what I've got in my inverse Fourier transform with that k-space line is I've got this nice vertical line here. Okay, so that's shown in top left corner, because this is the inverse Fourier transform of that k-space line, and so is this. And now we know from the central section theorem that this line here is meant to match that line there, the same k-space line from the 1D Fourier transform for phi is equal to 0. So does that make sense? Well, let's consider that's phi is equal to 0. So phi is equal to 0 corresponds to this vertical projection. If we were to vertically project this, then sure enough we'd be summing along that line there. And because we're showing it as a 2D function, then we end up just basically ending up with this vertical line when we represent that 1D function in the 2D domain. In other words, when we take this and then we inverse Fourier transform it, it should be no surprise that we get this result here. So if you want a bit more insight into that, then just consider again that what I'm showing in the top left and in the top right is the inverse 2D Fourier transform of just that red line here, okay? So how would we get the inverse Fourier transform? Well, we could do it a couple of ways. Well, one way of thinking about it is we could just inverse Fourier transform each of the rows here first of all. Well, if we were to do that, and if we're only inverse Fourier transforming that line, we're disregarding the other parts of k-space here, then inverse Fourier transform of that, that's just the 0 function, we'd end up with just zeros. So all of these rows, inverse Fourier transformed, if they're not being considered, they're 0, and so we just get a 0 result. Then suddenly when we inverse Fourier transform this, what would we get? We'd get a delta function at the origin, okay? And then as we consider the other rows, inverse Fourier transform those, again we'd get 0. Then, to continue to do the 2D inverse Fourier transform, we need to inverse Fourier transform next the columns. So again, remember we had zeros out here, and so those would all be 0. But then suddenly that delta that we mentioned earlier, if we inverse Fourier transform that, we would get a constant function vertically in that column that we're inverse Fourier transforming. So that's exactly what we see there. And then we consider along those other values, and they would be, again, 0. Alternatively, if you want to see it another way, we could start off by saying, well, let's inverse Fourier transform, first of all, the columns. Okay, so let's do that. So imagine, again, we're doing the inverse Fourier transform with just that center constant line in k-space. Let's inverse Fourier transform along the columns. So if that is a solid filled-in line, then that would be a delta function along this column. If we inverse Fourier transform that, we'd get a constant vertical line in the inverse Fourier transform. We'd do that for all of these, and we'd end up with a completely uniform image, okay? But then we've got to inverse Fourier transform to continue to do the 2D inverse Fourier transform. we've then got to inverse Fourier transform all of the rows. So what happens then? Well, remember we've generated that flat image. If I inverse Fourier transform all the rows, each of the rows is a constant function. Inverse Fourier transform each of those, we get a delta at the origin for every single row. And so sure enough, that's exactly what we see here, just a vertical line. So I hope you can therefore see that the inverse Fourier transform of this solid single line in K-space has to be this perpendicular line in the 2D image domain. Anyway, that was just to give a bit more insight. What we're saying with the 2D central section theorem is that that line in K-space is equal to this line of the 1D Fourier transform of that row of the sinogram, and it's exactly what we'd expect because this row of the sinogram is a 1D parallel projection, which is the vertical viewing angle, and that of course corresponds to this, if you like, this is just like a back projection. It's saying take the value, the integrated value along that direction, and just paste it all the way back down through the image to get a 2D representation, a back projection of that 1D parallel projection. Anyway, let's move on to the next direction in K-space. So now we're going to do the KY direction, and this is the KY axis. So now we're staying now at KX is equal to 0 at the origin, and we're going to progress up and down in the KY direction. KX is equal to 0. So that means now we've got a constant value in the X direction. KX is equal to 0, constant value. But now ky is equal to 1, therefore we've got 1 cosine vertically. Sine, kx is equal to 0, but now we've got 1 sine wave in the vertical direction. So that will become clearer as I progress upwards along the ky axis there. And you'll notice that as I'm populating that ky axis, I'm also showing by the central section theorem, this corresponds to this line through the 1D Fourier transform of that row of the sinogram, the pi over 2 or 90-degree view of the sinogram. Okay, so let me just progress upwards through ky. As I'm increasing the positive frequencies, I've got the cosines and the sine basis functions. I'm adding them together in the top right corner there. And so now you can see again, we're getting this kind of convergence, this constructive interference rather, at the origin of these sines and cosines as they're being added together, and the tails are cancelling out. Why is that? Well, it's because I'm taking constant values of coefficients for the sines and cosines. Okay, so I'm adding together all the spatial frequencies with equal, I'm adding together the spatial frequencies with equal importance, equal weighting for each of them. So let's keep going there. Now we're going to consider the negative spatial frequencies, so ky negative. Kx is still 0, Kx is still 0, but now I've got the negative ky, so 4 cosines, 4 sines, adding them together. Now as a reminder, here I'm showing just the inverse Fourier transform or the image domain representation of this line only that I'm forming, whereas in the top left corner, I'm considering the inverse Fourier transform of all of the red areas here. So the previous K-space line plus the current one, and that's what I'm forming there. Okay? So let's keep that moving. Negative ky values, and I'm also showing in the 1D Fourier transform with the sinogram here, I'm showing those same regions. And you'll see that as I again approach the Nyquist, where I've now got 64 cosines fitting vertically, you can see that the inverse Fourier transform of that line is now this horizontal line. Okay, that makes perfect sense because this is the 90-degree viewing angle. So imagine the XY coordinate system here rotated now to 90 degrees. It means I'm correspondingly taking projections of this point source, okay, in the horizontal direction. If I project that in the horizontal direction, this is what I'd get, okay? So it's that center row of the sinogram. If I were to back project that, I get this line here. Okay, so that's the, and I refer you to the discussion that I gave earlier if you want more insight into why the inverse Fourier transform of that vertical line in K-space corresponds to that horizontal line. And meanwhile here, I've just continued to build up the Fourier synthesis. It's the summation of the inverse Fourier transform of that line and that line. Inverse Fourier transform is a linear operation. And so we get this kind of intersection, this kind of back projection effect. Okay, and we could carry on with this, but now we're getting to the more interesting case of considering simultaneously kx and ky. So if kx and ky are equal to 4, I get 4 cosines along this direction and 4 sines along this direction. But now as I progress up the y-axis here, I now, due to ky being non-zero here, I actually end up with a phase shift for my cosines. If I consider them defined only with respect to x, then each y position corresponds to a differently phase shifted cosine. So that's what I'm seeing there. Likewise, as I progress vertically here, I'm getting a different phase shift for my sine as a function of x. And so that is why, as we progress in this diagonal direction in k-space, kx, ky mapping each other, then you're getting these kind of diagonal projection directions, if you like. And then as I'm superimposing them, I'm getting this nice diagonal line there. Okay, and then, so here I'm just not completely filling k-space. It's because I want to match up here with the simple Fourier transform with the sinogram. And so what I'm going to do here is just progress negatively out here. Okay, so again, you're getting these these diagonal cosine and sine basis functions. Adding them all together, I get this result here. So this, okay, is the inverse Fourier transform of that line there. Now, because I'm not going to the extreme corners, therefore we don't get this perfect diagonal line here. But you can see they've all constructively interfered in the middle, and the tails are largely cancelling out. And then meanwhile, I've inverse Fourier transformed the entirety of things here. And so that line in k-space is corresponding to that back projection, if you like. So we could carry on with this. I think you're getting the idea now. I'll try and let it run a bit more quickly now. What I'm basically doing is populating k-space and showing how those values in k-space directly correspond to values in the 1D Fourier transforms of all of the rows of the sinogram. And so I could just keep on populating k-space, and what we end up with here is a back projection. Now here, to deal with the need to normalize for varying contributions, what I'm just doing is simply checking whether or not I've already visited that location in k-space. If I have, then I'm not re-including it. And so that's why when you look at this, you can see which ones I've actually left out. So when I did the first one, I needed all of them, but as I'm doing these other ones, you'll notice that they've skipped the center point in k-space because it was already found from the first projection. Now, of course, if you were to implement this in practice, you would not do that. You would actually take all your data, do all the Fourier transforms, and then what you do is populate k-space and then normalize for the varying contributions. Here I'm just keeping it simple for the animation. But I hope you can see that what we're getting as we're visiting each line in k-space, we're getting these kind of perpendicular oriented basis functions, which when added together correspond to pretty much what we'd expect. So this is for the case of the point source. The benefit of this simple example is that a point source in k-space is this uniformly filled k-space. Okay, capital F is the same value everywhere. And you can see this nice kind of back projection result forming in the top left corner. So what I'll do now is to move on to finish with a more interesting example of the brane distribution. So let's do that next. So I'll finish then with this 2D example here. And what we can see is now we've got the 2D k-space for this brane distribution, and I'm progressing through k-space as we saw before, positive kx, negative kx, and what we're forming here are the projections, okay, and of course this line in k-space corresponds to that line in k-space. Then I'm considering the 90-degree viewing angle here, 90-degree viewing angle there. Those are a perfect match. And again, it's nice to see that that k-space line gives this projection in that orthogonal direction there, as expected. This is the superposition in the top left corner. Then I'm doing this diagonal line in k-space. That's the pi over 4, 45 degrees line, and so that's this row of the sinogram here. And when I do the other diagonal, then again I'm getting the projection in that direction as expected, perpendicular to that k-space line, adding them together here. And so you can see that as we proceed, we can fill up all the various radial lines in 2D k-space corresponding to extracting various rows of the sinogram, Fourier transforming those to find the values in the 2D k-space. And so this really is a visual demonstration of what is going on with the central section theorem. And again, in practice, what we'd need to do is normalize for varying contributions here using a ramp filter prior to inverse Fourier transforming. Or indeed, what's done with filtered back projection is that you'd Fourier transform each row of the sinogram to get this. Then you would do your ramp filter, so you'd amplify according to the magnitude of k. This is the center of k space down the middle there. So we'd ramp filter each and every row. Then we'd inverse Fourier transform that, and then we'd back project. And hopefully you can see from these graphical examples why the back projection is working, because that's corresponding, if you like, to that zero frequency, which kind of takes a delta function and kind of like spreads it out to a constant function, which is exactly what back projection is doing. So I'll let this run so we can follow it through to hopefully a good graphical conclusion. So I hope you found this video useful for understanding filtered back projection, and in particular the central section theorem, which explains the mathematics behind filtered back projection. Thanks very much for listening.